Let's consider Coulomb's law. Coulomb's law states that the force of attraction or repulsion between two charges Q1 and Q2 is proportional to the product of the two charges and inversely proportional to the square of the distance separating them. Let's write it down. Yeah. Coulomb's law states that the force of attraction or repulsion between two charges Q1 and Q2 is proportional to the product of the charge, that is Q1 times Q2, and inversely proportional to the square of the separating distance. Mathematically, we can easily deduce from the law that the force of attraction or repulsion, as the case may be, is directly proportional to the product of the charges Q1 and Q2, but inversely proportional to the square of the distance separating them, which later becomes F is equal to K. We will remove the proportionality symbol and replace with equal to and a proportionality constant. So we have K Q1 Q2 all over what? R squared. Where is this coming from? We can have two bodies, 1 and 2, with charges Q1, Q2. The distance between them is R. So from here, we can have our force of attraction or repulsion to be equal to proportionality constant times Q1 times Q2 all over the square of this separating distance. So that was how we got this. Please note that K is equal to 1 all over 4 pi E naught. And that's equal to 9 times 10 raised to the power of 9 Newton meter square per Coulomb square. That's the unit. Take note. The constant is this. That proportionality constant is expressed as this. Take note. Then also note that E naught, which connotes permittivity of a free space, is equal to 8.85 times 10 raised to the power of minus 12, which should be in a Coulomb square per Newton per meter square. Yes, or it can be expressed as farad per meter. Take note of this. If you substitute this value here now and you point your calculator, you will definitely get 9 times 10 raised to the power of 9. That's how it works. All right, let's consider electric field. Electric field. How do we define electric field? Electric field is defined as the region of space over which the force due to charge is felt. It is the region of space over which the force due to charge is felt. That's electric field. Another thing you need to know is what we call electric field intensity. Electric field intensity. Mind you, electric field intensity E is otherwise known as electric field strength. Take note of it. How do we define electric field intensity? Electric field intensity is defined as the force per unit area at that point. Which point are we talking about? Point in the electric field. So electric field intensity is the force per unit area at that point. The force per unit area at that point. I don't think there's any need to write that. You just know that electric field intensity is the force per unit area at that point. Mathematically, it's expressed as E is equal to force per unit charge. Per unit charge at that point. So this is it. And it is measured in, force is measured in Newton, then charge is measured in Coulomb. So it's Newton per Coulomb, like that. Please take note of that. This is very, very important. Then another thing you need to know, You need to know the electric field intensity due to a point charge at a distance. So electric field intensity due to point charge at a distance away is expressed as this. You know that E is equal to F all over Q, right? And from Coulomb's law, we know our F is equal to KQ1 times Q2. I can just say QQ all over R squared. Now divided by, what do we have at the denominator here? Q. That could connote KQQ over R squared. The division here will change to multiplication, and we have 1 all over Q, so that this Q will cater for one of these, and our electric field intensity due to point charge at a distance away will now be what? KQ all over what? R squared. This is another formula that you can use to solve. So I've given you two different formulas to solve. So that's that about that. Then another thing you still need to recall is that from electric potential, you have V is equal to electric field strength or electric field intensity times the distance D. So from here, you can easily make electric field the subject of the formula. Electric field intensity is subject formula, which will now be equal to V over D. And the unit here will be in volts per meter. I just say volts per meter like this. So please take note. This is the third formula we can use to calculate electric field intensity. It's very important. Let's take questions. But before the question, I want you to recall from our previous video that like charges repel, but unlike charges attract. If we say like charges, like positive, positive, they will repel. But positive, negative are unlike charges and they will what? Attract. Look at this question. Let's see question 1. Question 1 says, the force of repulsion between 2 point positive charges, that is positive, positive, hence the repulsion. The force of repulsion between 2 point positive charges, 5 millicoulomb and 8 millicoulomb, separated at a distance of 0.02 meter apart is, how do we approach this question? It's very simple. Solution to this question goes thus. You just recall Coulomb's law that says F is equal to KQ1 Q2 all over what? R squared. And what are we looking for? We are looking for the force of repulsion. So from here, we know that our K is equal to, is a constant, which is 9 times 10 raised to the power of what? 9, multiplied by Q1 was given to be 5 millicoulomb. Is 5 milli is 10 raised to the power of minus 3 coulomb, times the other one is given as 8 milli, that is times 10 raised to the power of minus 3 as well, all over the separating distance. That's 0.02 squared. Let's point the calculator. Our answer is 9.0 times 10 raised to the power of 8 Newton, which is option B. Please take note of this. This is very important. Question 2 says, the electric field intensity in a place where a charge of 10 raised to the power of minus 10 coulomb experiences a force of 0.4 Newton is, this is as well very easy to solve. You recall that your electric field intensity is equal to F all over Q, force per unit charge. And here you are required to get the electric field intensity. So the force was given to be 0.4, while the charge is 10 raised to the power of minus 10. This is very straightforward. That will give us 0.4 times 10 raised to the power of 10, which is equal to 4 times 10 raised to the power of 9. And that is option C. Let's consider electric potential. What's the symbol for electric potential? The symbol for electric potential is V. Then how do we define electric potential? It is the energy transformed in bringing a unit positive charge from infinity to that point against the action of the field. I should write. So electric potential V is the energy transformed in bringing a unit positive charge from infinity to that point against the action of the field. So that's that about that. And mathematically, V is said to be equal to electric field strength times distance. And from here, this is the first formula. Then from the above, we can say V is equal to, what is E? E is KQ over R squared. Then this D could be substituted. You know, is distance. R also means distance, so I can change it to R. This will cater for one of these. Therefore, our V will be equal to, V connotes electric potential. Please have that in mind, which is equal to KQ all over what? R. This is another formula you can use. Another formula you can use. So that you use the first one and the second one, depending on the parameters provided in the question. So that's that about that. Let's quickly consider the term capacitor. 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 Capacitor is otherwise known as condenser. So we can define it as a condenser that stores electric charges or electrical energy. Capacitor is a condenser that stores electric charges or electrical energy. That's the first thing you need to know. Symbolically, it is represented as this. I told you this in our previous video, which was simple AC circuit, when we're dealing with RLC. This is a symbol of capacitor. Why is it like this? Capacitor consists of two plates. Two plates. Like this. I can call this. This will be plate 1. This will be plate 2. Which is separated by an insulating material we call dielectric, where we have the plate 1, plate 2, plate 1, plate 2. That is why it's symbolically expressed as this. Take note. I believe you won't forget this again. All right. Still on capacitor. Capacitor is having a property we call capacitance. And the capacitance of a capacitor is having the symbol capital letter C, and it is measured in farad. We measure capacitance of a capacitor in farad. Take note. And it can be calculated using the formula, that is capacitance of a capacitor is calculated using the formula Q all over V. Q all over V, where your Q connotes the charge on either plate. You know it's having two plates. The charge on either plate. Charge on either plates. Why the V there connotes potential difference between the two plates. Potential difference, PD, between the two plates. Please take note of this. Then for a parallel plate capacitance, for a parallel plate capacitance, for a parallel plate capacitance, we use this formula. C is equal to permittivity of a free space, that is E naught A all over D. This works best when the space between the two plates is left empty or is filled with air or vacuum. We don't use any insulating dielectric material to fill it up. We use this. But when the space between the plates are filled with dielectric materials, such as mica, paraffin, sheet of paper, glass, etc., we will now have it as the C will be equal to K E naught A all over D, where the K here connotes the dielectric constant, where K connotes dielectric constant. You know, the dielectric constant for air is 1. It's more or less insignificant here. That was the reason why we did not put K. But let me just give you some basic dielectric constants. Dielectric constants of paper is 2. Dielectric constants for paraffin, like paraffin wax, is 2.2. While the dielectric constant of glass, well, depending on the type of glass, is 8 or thereabouts. Please take notes of all this. Now, what are the factors affecting capacitance of a capacitor? Factors affecting capacitance of a capacitor. Number 1, from the formula I gave you, C is equal to K E naught A all over D. From here, we can say C is directly proportional to area. Capacitance is directly proportional to area. That's 1. Capacitance is inversely proportional to the separating distance between the plates. Then capacitance is directly proportional to the dielectric constant. So from here, we can say the higher the area, the higher the capacitance. The higher, I don't need to write that. The higher the area, that's number 1. The higher the capacitance. Number 2, the lesser the value of the separating distance, the higher the capacitance. The lesser the value of the separating distance, the higher the capacitance. Then the third one, we can say the higher the value of the dielectric constant, the higher the capacitance. Or better still, we can put it this way. We can say the denser the medium between the plates, the denser the medium between the plates, the higher the capacitance. What am I saying? If the dielectric constant of air is 1 and that of paper is 2, so we can say paper is denser than air. Of course, air is less dense. So the denser the medium between the plates, that is the dielectric material, the denser the dielectric material, the higher the capacitance. Please take note of this. There's no way we talk about capacitors without having to talk about the types of capacitors. There are various types of capacitors. We have the lead-in jar capacitor, we have the fixed capacitor, we have the variable capacitor, and we also have the electrolytic capacitor. Types of capacitor. We have 1, we have the lead-in jar. We have fixed capacitor. We have variable capacitor, as well as electrolytic capacitor. You can take your time and read text on each and every one of them. So that's about that. Now let's see combination of capacitors, that is arrangement of capacitors. Yeah, there are 2 possible arrangements of capacitors. Capacitors can either be arranged serially, that is in series, or in parallel. Now, let me give you the diagrammatic representation of capacitors arranged in series. We have stuff like this. So this is a symbol that represents capacitors. So we have it like this for capacitors. So we call this um, C1. We call this C1, C2. For parallel, we have something like this. So diagrammatically, capacitors arranged in parallel are expressed as this. And we have our C1 and C2. This is a Q. So that's the first thing you need to know. Another thing you need to know is this. Talking about the charge for series, capacitors arranged in series. The same charge will flow through the first capacitor and the second capacitor because it's going serially. Look at how they are arranged side by side. So it's going to be Q is equal to Q1, which is equal to Q2. The charges across each of the capacitors are equal. So that's it. Equal to the total, the main charge that is entering the setup. So the charge across each of the capacitors are equal. So that's it. But in this case, charge Q will be equal to, at this junction, this node, it will split into two. One will go up, another will come down. So we're having Q1 here, and we're having Q2 here. So that when you add Q1 and Q2, it will give us Q. That's the first thing to note. The second one, in terms of voltage, you can say VT is equal to V1 plus V2. That is for capacitors combined in series. But when the capacitors are combined in parallel, we say voltage drop on each capacitor is equal to the applied voltage. Voltage drop on each capacitor is equal to the applied voltage. Hence, we say VT will be equal to V1 equal to V2. Please take note of this. Now, that brings us to equivalent capacitance. Equivalent capacitance. So, when the capacitors are combined in series, we use this formula to get the equivalent capacitance. 1 all over C total is equal to 1 all over C1 plus 1 all over C2. Then for parallel, capacitors arranged in parallel, we have CT is equal to C1 plus C2. Please take note of that. If you are not yet subscribed to this channel, please hit the subscribe button because I am having the fear of you missing out. Hit the subscribe button now and make sure you are subscribed to this channel. Like the video, then you continue to expect more wonderful videos from the Physics Classroom YouTube channel. So this is a convenient point to stop this before we now move to various questions under the topic electrostatics. See you in our next video.